let us begin the lectures on machine design part 1. This is lecture number 26 and the topic is design of joints with variable loading. In the last few lectures we have learned how to design the joint for strength for various static loadings. Now in the last class we have learned how to design the joint for eccentric loading, and in this class we are going to study for the variable loading. Now variable loading is very important for any machine components. In structural joints normally the loading is static, but in machine components there will be invariably some movable parts, and because of this movement there will be the forces which are normally fluctuating in nature. So these are to be taken care of while designing a joint typically for a machines. Think the example of a machine which contains a rotating member or reciprocating member. Definitely there will be the forces which are also oscillatory in nature, and that may cause failure because of the fatigue in the joints. So let us learn how to design the joints for variable loading. Now first we study how to design the bolted joints for variable loading. Now in connection with the joints of joints containing screws and bolts and nuts, we have studied a little bit about the variable loading. So here the discussion will be brief. We consider one example first. Let us take the following joint. There are two members which are connected this way. Now let us say this is one part and this is another component, and we have a bolted connection over here. So here is this bolt. And here the loading is, let us say here, which is the F external load, and that is fluctuating nature. So let us say the F external is something like this, little fluctuating nature. So here first of all we will have to find out what is known as the mean stress or mean force. Now mean force is found out once we know the maximum force. If we have F max, the maximum value, this is the maximum value, and the minimum value, F mean, this is the minimum value. So if you take the arithmetic average, then we call the force to be F mean force. Similarly, we can define what is the force amplitude, and that is equal to F max minus F mean divided by 2, and this is F amplitude. Now this data must be known to the engineer who is going to design such a joint. Now once this is known, then how to select the proper bolt, that could be done by standard techniques by different different criteria, namely the Soderberg equations or Garber line or Goodman's line. Let us discuss little bit the various things. Now here we have to know first of all what is known as the endurance limit. Endurance limit, normally SE. Now the corrected endurance limits depends on various factors. For example, it may be the nature of loading which is important. So, there is a factor for the type of loading. Normally, the endurance limit is calculated or is experimentally obtained by making some experiments with the bending. Now, if the loading is something different, then we will have to make some provisions, that is, make some corrections for the changed loading, and that is taken care of by introducing a load factor. Then there may be factor which is due to the surface finish of this component. So, the surface factor is there, temperature factor is there. So, all these things must be taken into account, and this endurance limit must be corrected. So, what we need is a corrected endurance limit. For the bowls, there are various specific corrected endurance limit for different kinds of bowls of different sizes. They are standard. So, we know this endurance limit. Of course, we know the stress concentration factor. Now, this is again fatigue stress concentration factor. Fatigue stress concentration factor, this is Kf. So, this must be known. Now, concentration factor, we have theoretical concentration factor, but when the material or the component is subjected to fatigue loading, then the fatigue concentration stress concentration factor is not equal to the theoretical stress concentration factor, and we have to take into account what is known as the notch sensitivity. So, when everything is taken care of, then we can find out what is known as the fatigue stress concentration factor. Again, there are various values available for Kf, and those are given in the machine design handbook. So, these two things are known. Now, we can go for designing. First of all, we will have to find out we will have to see which criteria we should use. Here we plot in this axis sigma m, which is the mean stress, and this is sigma amplitude, this is the stress amplitude. Now, sometimes sigma, for this case, if the external load is given, then we know that the load acting on this bolt will be equal to the external load fully if there is no pre-tensioning, but if there is initial tension, then it will be initial tension plus a factor multiplied by F external. So, this is a fraction which fraction of F external which acts on Fb. So, first of all, we will have to find out sigma m, that is sigma mean, with this Fb, that is the bolt stress. Now, F external is variable, F initial is normally constant. So, it is not varying, pre-stress is of course a constant value. So, sigma mean will have to be calculated from here. Now, that will be equal to Fdb divided by A of bolt, but in the normal design procedure we do not know what is AB. So, we calculate sigma mean in this form Fb, Fb is known, AB is not known, that is our aim is to find out this AB. Similarly, we can write down sigma amplitude as Fb. So, this will be the mean of that, and this is Fb amplitude and divided by AB. So, we will have to find out the Fb mean and Fb amplitude and then write down in this form. Then we will have to select the criteria. Now, there are several criteria. See, there is one thing which is called the Soderberg line, which is a line where this maximum limit is endurance limit or endurance strength, and that must be fully corrected. Here this goes to the yield point Sy, and then this is the yield stress. Depending upon the stress, depending on the type of loading, the yield stress may be different. If this axial loading and that is pure tensions and pure shear, the yield stress will be totally different. So here the criteria is that, so this is known as Soderberg line. Now we select what is known as a factor of safety. Now the criteria is that we will have to design such a way that if this is the factor of safety we have chosen, so now the design data, that is sigma amplitude and sigma mean, must fall within this line. So what is that? This is a fraction. So now this point SE prime, SE star and SY star. So SE star will be SE divided by some factor of safety. Similarly, Sy star, which is this value, Sy star, let us say, it will be Sy divided by factor of safety. So all the design data must fall within this line. For bolted joints, normally the factor of safety is from 1.5 to 2. So once we choose the factor of safety, remember this is a reliability factor. In order to make it make the joint reliable, so we select factor of safety and we find out SE star and SY star. Then the design criteria is that this must, that is the sigma mean divided by Sy star, which is equal to Sy divided by factor of safety, plus this is the equations of this line, particular this line, it will be equal to sigma amplitude divided by Se star, which is equal to Se divided by factor of safety. Here we have to multiply by this fatigue stress concentration factor Kf, and that will be equal to 1. So now F sigma m is again written in terms of F external, Fb and AB. So from this equation we can find out AB. So this is how we design according to the Soderberg line. Sometimes we use what is known as Goodman's line, and here the Goodman's line is, so this is one way. Now the next approach is to use Goodman's line, then this is joined from SE to S ultimate. Here previously in the Soderberg line it was yield strength, now it is ultimate strength, and again the same procedure, we have SU star, which is nothing but SU divided by factor of safety, and this line is the Goodman's line. So Goodman's line, then the equation is sigma mean divided by SU star, which is SU divided by Fs, plus sigma amplitude divided by Se star, and here again just like before we will have to multiply the stress concentration factor for this fatigue stress. So, again from this design we can find out what is AB. So, that comes from this equations. So, this is the Goodman's line. Again we have another criteria which is known as Gerber line, and let us discuss that. The Gerber line again is a line it is a parabola. So, this is the Gerber line, and again if you consider SU star and SE star, then the equation is written in this form, that is sigma mean divided by SU star, that is SU divided by Fs square plus sigma amplitude divided by Se by Fs equal to 1, and again just like before we will have to multiply by Kf. So, here you find that this is a this will give a quadratic relationship, quadratic equation in AB, which you have to solve to find out what is this AB. So, these are the different design techniques for bolted joints. We discussed it in some previous lectures. So, let us not give more time to that, but here we see the fatigue stress concentration factor, normal fatigue stress concentration factor for different metric grades. The metric grades are, here you see 3 points. So, there are various materials available, they are in ISO grade for 3.6 to 5.8. For the rolled thread we have 2.2 fatigue stress concentration factor, remember this is Kf. For cut thread it is 2.8, again because there are different this is a different procedure of making the threads. So, they will introduce different stress. So, therefore, the fatigue stress concentration factor, these two are different. If we have fillet, then we have 2.1, little less. For metric grade of higher grade, higher values, then the stress concentration factor is again higher. You see for the cut thread it is much higher, for fillet it is little lower side. So, these are roughly the fatigue stress concentration factor for the bolted design. So, now these are everything are tabulated. So, when you want to design such a joint, then you should make use of this these values, and those are given in the machine design handbooks. For fully corrected endurance strength, again we see for the different grades we have for different size M16 to M36. Remember this is the size of the bolt, metric grade for the nominal diameter, and the endurance strength, again it is fully corrected endurance strength 129 megapascal. If you go on to the higher values, then you see it goes on increasing. Okay. So, these are the fully corrected endurance strength, and those are given again in the handbook. So, you must know that such data exist, and you should use them while designing that. Now, let us come to the design of welded joint, which is very important, because in welding you will find the stress concentration is quite appreciable, because of various reasons, that is we discussed already. In the heat affected zone or during the welding process itself, some residual stress may be generated, or in the heat affected zone the metallurgical transformation may take place. So, this will all lead to some kind of stressing which will again lead to the crack initiations. So, if crack initiates, then it will propagate when the loading is alternating or variable. So, the stress concentrations will be important there. Remember, in the static loading, the stress concentration is not that important, because always there will be some plastic deformations which will take care of the such enhanced loading, enhanced stress. But if the loading is fluctuating, the stress is fluctuating, then the crack can easily propagate. So, this is very dangerous. For different weldings, we have different stress concentration factor. So, we have what is the Kf for here. Now, it also depends, you see, for different kinds of weld also. It is not the material property for different kinds of welds. Here, take an example of a butt weld. If you have two such pieces which are welded, butt welding, then you see that there is an abrupt change in the cross sections. If we apply a load here, then due to this abrupt change, if you find out the stress distribution there, then the stress distribution is not uniform, but it will be of this kind of nature. So, this is the stress distribution. Now, how to avoid that? We do sometimes we cut it off, that is here, and we remove this part. Similarly, we remove this part. So, then the stress concentration may be reduced. If we have a fillet joint, then the stress concentration is again quite important. If you consider a fillet joint, let us say we have a fillet joint given this form. So, this is one bar connected to. So, let us apply a load twice F, it will be taken F, and remember the fillet is here. Now, after careful experiments, it was found out that if you consider this fillet, then the normal stress distribution is something of this form. So, that is a positive normal stress and negative normal stress. You see the stress concentration appearing here. Similarly, on this side, the stress distribution is something like this. Again, this is positive. So, this is sigma. So, therefore, in this region, and this region, the stress concentration exists. There are various ways to decrease the stress concentrations. One is by making this shape concave profile, or if we increase the leg distance, that is normally this is 45-degree angle, but if we decrease this angle, that is make this larger than that, then the stress concentrations may be reduced. Nevertheless, there will be stress concentration always, and the typical stress concentration values are plotted here. For reinforced butt weld, this is 1.2, for toe of fillet weld, this is 1.5, for end of fillet weld, this is 2.7, for T-bar joint with sharp corners. Remember, the bar joints are possible, T-bar joints are possible, and so here we have 2.0 stress concentration factor. So, these are roughly the stress concentration factors which are again tabulated in the design handbooks. Now, with this data, let us try to design some of the welded joints for variable loading. Let us first consider this case. Again, we have a plate which is connected to another plate. By welding is done. This is again the fillet welding, but now this is parallel fillet or longitudinal fillet, the force is applied over here. Now let us see, let us take that this distribution of this force with time, let us say this is totally sinusoidal. In this case, you can find out this F mean equal to 0 and F amplitude is nothing but this amplitude. So, this is F A. Now, in this case, Soderberg line or Gerber line or what is called a Goodman's line will be of no use, because right now we are having purely fluctuating stress, purely oscillatory stress. So, therefore, we will have to consider the design. First we find out the stress. What will be the stress? Now, definitely here the stress is shear in nature, and if you consider this fillet, this is the fillet cross sections, but the critical cross section is not the entire cross sections, it is this sections. So, therefore, the shear stress, here we have definitely shear stress. The shear stress will be equal to F divided by the total throat area, that is 2 for each fillet, and AT, where AT is nothing but the length times the throat length, which is T, L times T, and this is nothing but 1 upon root 2 times H times L, where H is this height, the size of the welt. So, if we find out this tau, then definitely this tau, this maximum value of the tau will fall below certain limit. Now, what is that? Let us see, for the successful design we must have tau must be less than equal to then endurance limit. Now, here endurance limit is to be calculated for endurance limit for the shear stress, because now the loading is shear type. So, this is again corrected. So, we will have to take into account the load factor here. So, this divided by factor of safety, and what is that factor of safety? Factor of safety is normally taken to be 3 to 4. So, this is greater than 3, that is roughly the practice. Factor of safety is greater than 3, and then we have Kf, that is the fatigue stress concentration factor. So, we must have tau, that is tau is less than AC divided by factor of safety times Kf. Now, remember AC endurance limit is calculated, it is tabulated when the longevity is infinite, that is it will never fail. But if we want the loading for some time, then we may not be so restrictive in this design. We can find out the corresponding endurance strength for different loadings. So, normally if we have this SN curve, then the endurance strength will be, say, AC 1 divided by AC 2 will be equal to N1, that is N1 is the number of cycles in which it will operate, divided by N2 times a factor K. So, now this factor K is about 0.13 for butt joint and from 0.15 to 0.18 for the fillet joint. So, this is how we calculate this AC for, that is the allowable fatigue stress. We should not call exactly, theoretically speaking, we should not call it AC, but this is allowable fatigue stress for different number of cycles N1 and N2. So, this is how this design is done. Now, when we use this, then we can find out what is this AT, what will be the maximum value of this minimum value of this AT, I am sorry, and with this minimum value we can design what will be the minimum length H, or this minimum length of the weld H, or minimum length of this fillet, minimum length of this fillet H and minimum length of the weld L, to be precise. Now, this is done for the complete reversal of loading. Suppose we do not have complete reversal, then what to do? Then of course, we have to recourse to our original formulation, that is, in this case let us assume that F is not totally fluctuating, but something like this. So, then we can find out what is F mean and what is F amplitude. That comes from this F maximum value and F minimum value, which is 0 over here. So, we can find out F mean and F amplitude, and then we take the help of that Goodman's diagram, which we have already used for the bolted joints. Goodman's diagram again for sigma m, sigma a. We can use different strategies. We may use Soderberg line, where this is from sigma e SE to SY. Then this is Soderberg line. We may take another approach. This is with SU, and this is known as Goodman's line. Or sometimes with Garber line, which is this one. This is Garber line. There is, of course, this is the standard technique. We can write down the formula, that is, for the Soderberg line, of course, it will be sigma m divided by SY divided by factor of safety plus sigma a divided by SE divided by factor of safety, and here we will have to multiply by Kf, and that must be equal to 1. So, this is for the Soderberg line. If we use Goodman's line, as we have just, so here what is not known is this AT. So, that comes from directly from this expressions. Remember, sigma m is Fm, Fm is known, and that is divided by the total throat cross sectional area. So, we do not know what is AT, we want to calculate AT. So, here we replace sigma m to be Fm divided by AT. Now, you see, once you substitute Fm by AT in place of sigma m and Fa by AT in place of sigma a, then this equation gives the unique value of AT. So, from this we can design what is T or L or H, if that depends upon what you want. So, this is for the Soderberg line. If we use the Goodman's line, then we have, instead of SY, the only change is that instead of SY we have SU. So, this is now Goodman's line. When we have So now again we can get the value of AT. When we have the Gerber's line, then what is done here, the Gerber's line equation is nothing but square of that. So let me erase all these unnecessary parts. So this gives not the Goodman's line but the Gerber line. So from this, here if you substitute again sigma m and fm, what you get, the quadratic relationship in AT, which is to be solved. You take the maximum value of AT, and with this you calculate either L or H or T. H and T are related by this formula, that T will be equal to H divided by under root 2. So this is how the design is done in the normal way. There is another alternating way which I would like to discuss here. Again we take this same example, but now we want to discuss another way. This is what is known as using what is called this maximum allowable fatigue stress. For the weld. Here the approach is that we find out what is the maximum stress. Remember, we have the fluctuating stress component corresponding to F, and then we have then the maximum value of this F, and with this data we calculate what is the maximum fluctuating stress, and this maximum fluctuating stress, that is the maximum value of this fluctuating stress, should be below the allowable fatigue stress. Now how to calculate this allowable fatigue stress? Those are again tabulated, but there are various techniques in various countries. For example, in United States, the maximum stresses are tabulated in this form. First we calculate for the maximum allowable stress for repeated loading, that is the loading of this type, where the mean value is 0, that is the minimum value is F minimum will be here, and that is equal to 0. With this we calculate what is the maximum allowable stress, and that is again done by experiments, and then these values when is calculated, that is sigma max, let us say, this is divided by one factor 1 minus k. Now this k factor takes care of this asymmetry in loading. If k is defined as sigma mean, that is the minimum, divided by sigma max. If we consider one cross sectional area, the same cross sectional area, then this is nothing but F mean divided by F max. You remember here k will be equal to 0 in this case because F mean is 0. For the repeated loading of this type, so here k is 0 and the allowable stress is sigma max itself. For this kind of loading, sinusoidal, then F mean is minimum value of F is nothing but minus of maximum value of F. So therefore k will be equal to minus 1. K is plus 1, then this is not well, this formula should not be used, but remember for k equal to 1, minimum is equal to maximum, that is only the static loading, where of course we do not need to consider this this design procedure. So for different values of k's we have these values. So this is the allowable loading. For the variable loading case, this is the allowable stress, and the maximum stress here should be lesser than this allowable stress. In Russian literature, of course, the procedure is little complicated. What we have there is, again, we calculate what is the static stress, and that is maximum value for the static loading, and multiply by a factor gamma. Then this gamma is, it looks a little complicated. This is something, there are few factors, k sigma minus b, there may be plus or minus depending upon compression or tension. Then this is a k sigma, then the reverse, and times this k is again defined this way. So gamma is definitely less than 1. So the value allowable stress is gamma times St. Again, if the number of cycle is not infinite, infinite means more than 2 million cycles. If it is less than 2 million cycles, then of course this k sigma, that is the stress concentration factor. Remember, this is k sigma is nothing but stress concentration factor, corrected stress concentration factor, and those are again multiplied by another factor, and then this is how the effect of number of cycles is taken care of. Then again, ultimate design objective is that sigma maximum, that is the maximum value of the sigma, must be sigma less than sigma a. So this is roughly the procedure. In Indian design handbooks, you will find again these kinds of, well, the values are given for various size, like the tension, fillet weld for tension, for compression. So they are given in the form of tables. Normally they look like some value sigma divided by 1 minus 2/3 k, where this factor is 2/3 now, and k is the same. So once you know this sigma for different value type of loading, you may calculate what is the corresponding k, and then with this we calculate the allowable fatigue stress. For grouped bar joints, for tension again we have some thing. Normally this is 1 minus k by 2 something, where these values are again tabulated. Everything is tabulated, so we look for that particular data for to calculate what is the maximum or allowable fatigue stress. So remember, the maximum design stress must be less than maximum fatigue stress, allowable fatigue stress. So this is the design criteria. Now for this type of joint, it was relatively simple. If you consider another little complicated joint, so if you consider somewhat complicated joint like this, fillets are all around, and this is subjected to a load something like this, and this is again fluctuating in nature. Now how to use that conditions? Remember, we studied in the last class that here the effect, this kind of joint will have two kind of shear stress. The shear stress which is the primary shear, that will be equal to tau will be equal to F divided by the total throat area, that is the throat area for this entire length, the entire throat area. So this is the primary shear stress. There will be secondary shear stress, because Now because of this kind of loading, that is eccentric loading, it will try to rotate about its center. So there is a tendency of rotations. So what will be the stress developed? Again, just like what we have done in the last class, this part will have a stress tau 1, let us say tau 1 will be proportional to the magnitude will be proportional to this distance r1. So similarly we can find out what will be the stresses individually at various locations. The proportionality constant can be found out from the technique which we had discussed before, but the end result is that we know what is the secondary stress for various points. Now if you consider a small section, let us say if you consider this section enlarge little bit, then what you have? You have the direct shear tau and the shear tau prime. Then we calculate what is the resultant. Now remember, we cannot find out the resultant stress vectorially, but what is done is that this area is constant. So the force will be equal to this times dA, the small area, and this times dA will be the force over these sections. So therefore this resultant force is tau times tau resultant dA. So therefore the resultant stress is tau resultant dA divided by dA will be equal to tau r. So now we calculate what is the maximum as a resultant stress. We make these calculations for various points. For different points we make these calculations. So we know the secondary shear force and the primary is always there. So therefore we calculate the resultant shear force for all the points, and we calculate the maximum shear stress acting over this section, and then this maximum value will be less than equal to this allowable stress. That is, what we now have is tau r, the maximum value must be less than this tau allowable. Again this is for shear only, for shear only. So this is how this kind of joint this kind of joint is to be designed. Now if we have another kind of joint, let us say a joint where different kinds of stressing is possible. Remember, up till now we have considered only those joints where the loading is of uniform nature, that is either shear or in tensions. But suppose you consider this kind of a joint. This is another plate. Now here we apply load this way F, but now the welding is here in these sections. Or in order to make it much more precise, we may take a little variation of this example. Let us consider a cantilever beam where the welding is done over this part. Now what will happen here? Here you will have the direct shear stress first. So this tau will be equal to F divided by AT. So remember, if we look from this side, then we have here, and this weld melts are on these two sides. Remember, the entire load will be carried by this weld melt, this part. So, we have the shear stress here acting, direct shear, and there may be bending stress. So, because of bending there will be the tensile stress. Now, because of bending, then sigma will be m. The maximum bending stress will be here. If you consider this to be length b, then m b by 2 divided by I. What will be the I? I will be the I of this welded region only the weld. And remember, here we must take the critical cross sections, that is, instead of taking the true size, we must take this size to be T, that is the throat length, which is equal to h divided by root 2. Then with this configurations, geometry of this cross sections, we calculate what is I, and this will give the value of sigma. Now, in the endurance limit, there is load factor. So, load factor will depend on whether this is tensile load or shear stress, but here we have both kinds. So, how to do that? This procedure is simple. We calculate the equivalent normal stress using von Mises criteria again, sigma square plus thrice tau square, and then we calculate the entire thing again only considering the tensile stress. Just now we can ignore this shear stress because we are now dealing with sigma prime, which has already taken care of this tensile of this shear stress. We can also use the maximum shear stress theory, that is tau max. We calculate, and that will be equal to, of course, is very known, this is under root sigma by 2 square plus tau square. Then we can use this theory as well, tau max. So, we can reduce this multiple loading to unique loading if you consider the maximum shear stress or von Mises stress theory. There is another way which is sometimes used, that is, instead of taking to be sigma here, that is, there is one way, that is, we calculate the same, but taking this to be again another tau. So, instead of taking this to be sigma, we take this to be a tau and make this calculations, that is, the total stress will be this plus this together. So, the total stress will be T total is tau plus tau direct, that is primary, plus tau due to bending. Then we can use this formula. Now, here we see that the factor of safety is little larger if you consider this. Therefore, this is much used, and this is mostly used in Soviet Russia and many other countries, but this gives a conservative value. So, now we have learned various ways of calculating designing the joints for the variable loading. So, there are few techniques, two techniques at least for the welded joint, namely the usual Soderberg, Goodman or Garber line criteria, Garber lines, but there is another technique using the allowable fatigue stress. So, the maximum design stress will be less than this allowable fatigue stress. So, this is how normally these welded joints are designed. So, now in this class we have learned how to design bolted joints and welded joints when the loading is variable, and that is very important. You should read many books on the same topic and try to solve some problems. So, that is all for me today. Thank you very much.
Good day. Today we start our lecture, which is lecture number 27, and this is did the design of springs. Now, for the design of springs, we start with the how we define basically a spring. All of us know what is spring, we have used springs in everyday life. So, basically we can say that springs are used as a flexible joint between two parts or bodies. Now, here you are having some sort of objectives for the spring. What is that one? First of all, to cushion, absorb or control energy due to shock. This is a very common thing what we find out, the application of the springs in car springs or railway buffers, and to control energy due to shock is a well known situations for the springs, supports and vibration dampers. Next, to control motion. What is this idea to control motion? Means maintaining contact between two elements as cam and its followers. You understand that when if you just think of the cam and follower arrangements widely used in so many applications, then you will be finding out a spring is there which always keeps the contacts between the cam and the followers, thus it controls the motion. Now, whenever you see someone driving a car, he uses a brake or a clutch for the car control of the car control as far as the motion is concerned, and there what you do, you apply a brake which again eventually is having a spring system, and the clutch is also having a spring system which engages and disengages, aided with the mechanism of a system of springs or a single spring like that. And another one is the restoration of a machine part to its normal position when the applied force is withdrawn. A typical example, you know, that in turbines, in the turbines, suppose if we take an example, then what we see that whenever you are having to control the speed, okay, which is going on increasing or decreasing, a governor system is used which controls the motion or the rotation of the turbine wheels, and thus say the flow through the turbine vanes by the governor mechanism, which controls a series of say vanes for inlet water impingement like that, and that is also controlled by springs. And here we use again as in some sort of a control motion, and that is also using a spring governor. And another example, that some valves, actuator valves are also having the spring which can have some arrangements for the control motion.